Okay, in last class we have seen advantage of dielectric resonator antennas over patch antennas. In today's lecture, we will talk about uses of dielectric resonator antenna as sensor. We have designed dielectric resonator antenna in cylindrical shape, as we see here, as blood glucose sensor, and we have designed this CDRA at 8.72 gigahertz. There is a formulation of standard design, and there are resonant modes, as we have discussed in the previous class, that we want to excite fundamental mode or higher order mode depending on the design dimensions of CDRA. If you see here in this diagram, this is CDRA of material TMM, and the CDRA is under measurement for resonant frequency. If you see this graph, there is a S11 and it is showing that its resonant, the peak is at 8.72 gigahertz. So based on dimensions, we have theoretically computed the frequency of CDRA. It is 8.72, and same we want to verify or validate with the measured results using VNA in our lab. And it is, if you see here S11, it is coming almost 8.72 gigahertz. So now we want to use this CDRA as blood glucose sensor. Let us see how we can apply the CDRA for measuring blood glucose level of healthy or unhealthy person. How we have done? We have placed our thumb on the CDRA, and then we have measured shift in frequency depending on the permittivity of the thumb, or you can say blood level. We calibrated that thumb with certain formulations being used, and then we could say that how much is the shift in frequency as far as S11 is concerned. Then based on that shift in frequency, we will be able to predict the dielectric constant of our thumb, and based on that dielectric constant of healthy or unhealthy, we will be able to calibrate how much is the blood glucose level of that person. So CDRA we can apply as sensor. We have done for blood glucose. Similarly, we can use the CDRA for measuring different parameters like temperature, pressure, and other parameters which are biomarkers can be used. Now in this CDRA, we have worked on microwave frequency. Similarly, we can switch on and we can go up to terahertz frequency. The second application of DRA we have made to use this CDRA at frequency 456.5 terahertz. But this sensor is being applied for different applications, because in our retina we have rods and cones. So we have taken shape of rod which is cylindrical in nature, and then this rod shape DRA is being used as retinal prosthesis application. Reason being, in our retina, in periphery we have gray color cylindrical shape DR sort of, but there are some different layers in our retina, and these are specific to light wavelength. With this, when the photon falls on retina, because of it, the photon gets converted into impulses, and these impulses are wavelength specific. So these are getting converted into impulses, electrical impulses. Then these electrical impulses travel to the optic nerve, and based on the signal which travel to optical nerve, it stores into the brain. So we are able to get this DRA to convert the photons into a particular wavelength, and then it gets converted into visual content. Similarly, if you see central part of our retina, there are cone-shaped DRAs. We have worked on different configuration of cone-shaped DRA in the next one, but these cones are specific to RBG wavelength. So as artificial vision, we can apply these cylindrical DRA as well as conical DRA, because in old days these rods and cones are not able to give sufficient impulses. Then we, by using these cones and rods made up from DRA, we will be able to restore the sight of people who are in old age. So we try to mimic these DRAs in place of cones and rods which are being used to restore eyesight.